Given measure space, we considered the space of measurable and integrable functions. And now we want to see which structure of topological space or Banach space one can consider on the space of functions. And in general, we have many notions of convergence, and they might be different. And but the structures of Banach spaces is not going to be possible in the general setting of considering all possible measurable functions. So let's see what we want to study. So for a measure space, let's call it E, sigma algebra E mu is the measure. We consider, let's consider L of mu, or better L of E mu, the set of all functions from E to R that are measurable respect to the sigma algebra, and up to the equivalence relation of being the same almost everywhere. So with the equivalence relation of being equal mu almost everywhere. Okay, so what is something that is very clear is that this space here is a vector space. You can add two functions, you can multiply by scalars and by scalars in the real numbers, and this will stay measurable. Now, the question that we are facing at this point is this vector space a topological space? Or it's even a Banach space, it's complete. But from the definition, we have this just as a set. We don't know what is the topology that we would like to consider, right? And we didn't discuss any topology on this. What we discuss are notions of convergence, which is not the same of having a topology. Okay, so let's clarify the kind of convergence we consider. Okay, so let's take a function and then a sequence of functions from E to R, measurable. Then the first possibility of considering as a convergence, we said that Fn converged to F mu almost everywhere if there exists a set A in the sigma algebra such that the measure is 0, and for all x that is not in this set, we have that f of n x converge to f of x. Okay, and okay, I chose a representative for this function, right? But now if you change them up to a set of measure 0, one can see that up to changing the set A, you still have the same property. So let's note that this definition is independent on representatives in L mu. Okay, so now we have a notion of convergence. We should ask ourselves, is this coming from a topology? So again, giving notion of convergence does not give a topology necessarily. And in fact, this will be the case here. To let you understand what is going on, I want you to think of the following example. So here's a very illustrative example. I'm going to give functions. I'm going to consider functions in 0, 1 with the Borel sigma algebra and the Lebesgue measure. Instead of giving the formula for the functions, I will draw the graphs that are much easier to understand. So F1, okay, is the characteristic of 0, 1. So if this is 0, 1, and this height is 1, it's this function here. So this is the graph. Then F2 is going to be the characteristic of 0, 1/2, and F3 is going to be the characteristic of 1/2, 1. So again, the graphs is going to be, so this is 1/2, this is the graph, and then F3 is 0 first, and then 1. Then F4, so what we do next, we take the interval and we divide it into 2 to the n parts. So now next time we divide in 4 parts. And then first we take the characteristic of the first interval, then we will take the characteristic of the second interval, and so on. This characteristic of 0, 1/4, then the characteristic of 1/4, 2/4, and then we'll take the characteristic of 2/4, 3/4, and so on. So every time we're going to have a finer and finer, a smaller and smaller support that moves until 1, and then start again with a smaller support, moves up to 1, and then again continue. This is a sequence of functions. Okay, I don't want to write what is fn as a function of n, but this is the first elements of the sequence. Okay, these are functions that are for sure in this space here. Okay, the question is, does this sequence fn converges to anything? Now, first of all, okay, it's not clear if they converge, but let's see that we have as a subsequence we have the characteristic of 0, 1/m, and this sequence of functions, for sure, they converge pointwise, which converge pointwise to the function that is the characteristic of 0. So on 0 is 1, and everywhere else converges to 0. Okay, and this function is equivalent, mu equivalent to the 0 function. So which means that if the sequence converge, then it should converge to the zero function, because one of its subsequence converges to the zero function. Now, what is the general function doing? Let's again think of the definition. So Fn as a sequence is an enumeration of, so I will write it as a sequence with two indices. So it's the characteristic of, so what you do, you divide the interval into 2 to the n parts, and then you take, so n is a natural number, then we take another, so we choose an n and a k integers, and then we, so n is an integer, and then k is going to run between 1 and 2 to the n, and then we consider this interval here. See that we divide finer and finer, and then we move from 0 to 1. Okay, so this is written as a sequence in two variables, with two indices. So, and Fn is as a proper counting of these elements. Okay, so now as you see that this set here is getting smaller and smaller. So let's give a name to this set, A and K. Let's call it Mk. Is this set k minus 1, 2 to the m, k, 2 to the m. Now, let's take, so for every, what is the fact that for every sequence of points Pn, such that Pn is in AMK for some m and k, so we have that, so I'm thinking these points as points in the support of this function. But what we have that since, so these points are in 0, 1, and 0, 1 is compact, then there exists a subsequence, it's called Pnj, converging to P, 0, 1, as j goes to infinity, which means that this set, up to taking the subsequence nj, they are converging, this the middle, let's say that this Pn is the middle of these intervals, these Pn are converging to somewhere. Moreover, the size of this interval is getting smaller and smaller. So this observation makes us deduce that hence the respective functions characteristic of A, Mj, Kj converges mu almost everywhere to the function characteristic of P, if you want, to the zero function. So what we understood is that every sequence of an Fn has a subsequence, every subsequence has a subsequence converging to 0. Let's make this as a conclusion, and now we understand why it's important. There exists a sequence, which is the one that I defined in L infinity R of 0, 1, doesn't matter, put 0, 1, 0, 1 with Lebesgue, such that every subsequence has a subsequence that converges almost or near almost everywhere to 0. But the sequence does not converge to 0. Why? Because there is no set of full measure where the convergence is pointwise. Every point will be counted, will change from 0 to 1 back infinitely many times. And this makes us deduce that such a notion of convergence does not come from a topology. Because in a topology, if every subsequence has a sub-subsequence converging always to the same limit, then the initial sequence should converge to the limit. It's a very simple exercise in topology. So I'll write this as a proposition. There exists no topology on L. I'll write it R. It's the same example works, such that Fn converges to F mu almost everywhere, Lebesgue almost everywhere, say almost everywhere, if Fn converges to F in this topology. Let's continue our discussion about the possible notions of convergence of functions. So let's recall. So we have function, then sequence of functions from a set E into R. They're measurable with respect to on measure space. Okay, now I will list at least 5 different notions of convergence. So first, convergence is actually the strongest, is the uniform convergence. Uniform convergence, we say that Fn converge uniformly to F if for all epsilon there exists n natural number such that for all n greater than n and for all x in E, the difference between Fn x minus f of x is always less than epsilon. 2, pointwise convergence. So Fn converges to F pointwise if for all epsilon, and now what we allowed that the n depends possibly on x. So for all x, first we fix x, then we can choose an n such that for all greater n you have the same bound. now let's make this. So both of these convergence depend on the representative we choose for these functions. Now, if we change them up to a set of measure 0, they might not converge anymore. So let's change at least this one, pointwise convergence, up to a set of measure 0. So this is, we have the notion of almost everywhere pointwise convergence. So we said that Fn converges, see, mu pointwise to F if there exists a set A in the sigma algebra such that the measure of this set is 0 and for all epsilon, so we have pointwise convergence on the complement of A. So for any epsilon and for any x not in A, there exists n such that for all n greater than n, we have the usual bound. Okay, fourth type of convergence is the convergence in LP. P is 1 or infinity, between 1 and infinity. So this convergence, we said that Fn converge in LP to F if the norm of Fn minus F, the P norm, which I recall you is the integral of Fn minus F to the P, the power 1 over P, this goes to 0. Fifth and last convergence is the convergence in measure. Fn converge in measure to F if for all epsilon, which you think of an error, the measure of all those points for which we don't have this bound. So which means that Fnx minus Fx now is actually greater than epsilon. The measure of this set is infinitesimal, goes to 0 as n goes to infinity. Okay, now some obvious implications are, if you have uniform convergence, in particular, you have pointwise convergence, and in particular, you have almost everywhere pointwise convergence. Okay, so obviously, 1 implies 2, which implies 3. Now here's instead some less obvious implication. So if the measure of the whole set is finite, then we have 3 implies 5, namely almost everywhere pointwise convergence implies convergence in measure. Another one is going to be that convergence in LP implies convergence in measure. So convergence in measure is the weakest. So 4 implies 5. Another one is that if you have 5, namely if Fn converge in measure to F, then we cannot really say that we have convergence. So I would like to say the inverse implication of this. This might not be true, the inverse might not be true, but it is up to passing to subsequence. Then there exists a subsequence nj such that f and j converge mu almost everywhere pointwise to f. And to see that one has to pass to subsequence, one can consider the example that we discussed before as the characteristic of intervals that move. I will mention another result that is very important, and it's called Egorov theorem. That again, if the measure of the space is finite, and we have mu pointwise convergent to f, then we don't have uniform convergence, of course, but we have up to choosing an arbitrary small error. So for any delta, there exists a measurable set in the sigma algebra with the measure as small as we want, so less than delta. And now if we restrict the functions to the complement of A, which is a big measure set, not full, but big, then the convergence is uniform to F. Good. Now let's clarify what is the need of assuming a finite measure in some of this statement. Remark. So a pathological example. So it's an example that one should have in mind to understand that some things cannot be true. But the measure is infinity is given by the functions characteristic of n infinity. These are on R with the Borel sigma algebra and Lebesgue. What we have is that these functions here pointwise converge to zero function, but the convergence is not in measure nor uniform or almost uniform, because the measure of the set on which these two functions do not coincide, or the points where there are always a lot of points of distance 1. So this is an example to keep in mind. Let's prove just the first two implications that I stated. So I want to prove that if the measure of the space is finite and Fn converge mu pointwise to F, then Fn converge in measure to F. So we fix epsilon and we consider the sets Bn to be all the points for which there is some time in n after n for which the distance between f of x, fn of x, and f of x is greater than epsilon. And then we consider B to be the decreasing so it's the limit of this Bn, in the sense of is the intersections of all the Bn. So it means that are all points that are frequently satisfying this inequality. Okay. So by assumption, since we have that on a full measure set we have pointwise convergence, then the measure of this set B is 0. The measure of B is 0. On the other hand, okay, but now what is the measure of those points in E for which this distance is greater than epsilon? So this is less than so these points, this set is a subset of Bn, so the measure is less than the measure of Bn, and now the measure of Bn converges decreasingly to mu of B, which is 0. So we proved that we have convergence in measure. The limit is 0. However, let's pay attention that in this implication, we used, it's important, otherwise it's not true, it's important that the measure of the whole space is finite. Otherwise, one does not have this implication after this assumption, okay, after this property, okay? Good, so this is the end of the proof. Now, the second proposition to prove is that if Fn converge in LP to F, then Fn converges in measure to F. The proof is very simple and it relies on Chebyshev inequality. So we fix epsilon. Now the measure of those points in E for which Fnx Fx is greater than epsilon. This is by Chebyshev. Is okay. If you have this property, then let's put power p, which doesn't change this inequality. Now we apply Chebyshev, and we have that this is less than 1 over epsilon to the p integral of Fn minus f the p. So we apply Chebyshev to this function here and value epsilon p. So this is Chebyshev. And dx, and this is exactly going to 0 by assumption that Fn converts to F in LP. End of the proof. So for any fixed epsilon, this limit is 0.